Hi everyone, good morning. Welcome to the Construct. Today we have a presentation from Sam Daly. He's going to be showing us his final project for the course we offer here, ROS Basics in 5 days with Python. And he's going to show us what he did regarding three main topics, three main things. The publication and subscription of topics, the usage of services, and the usage of an action server. What he's going to do is work with the Turtlebot 3 here at our Real Robot Lab, and he's going to show us how he combined all those three things in order to create a program that makes the Turtlebot follow a wall, the wall in our lab around, while recording the odometry with the action server. So welcome, Sam. How are you?
I'm good, thanks. It's good to be here.
Great, great. So you have, let's say, around 20 minutes, and we can start with your presentation, and I'll be, if I don't understand something that I think might be helpful to others, I'll jump in and ask, and at the end,
Okay.
I'll also ask some questions, and so you have the floor, and whenever you're ready, Sam.
Okay, well, hi everyone again. The way I approached this project, ROSject, was a very heavily object-oriented approach. I basically did a lot of, implemented a number of classes in each on their own scripts and got them to accomplish one of the basic requirements. Some were just simple topic publishers, some were simple topic subscribers, some classes inherited these more basic classes, and then I put them all together.
Love that. Always do object-oriented.
Yes, I made kind of like, for once I saw like an actual use of the classes that didn't make them seem kind of strange to me. I'll just share my screen now.
Great, great.
Can you see that?
Just hold on a second. Let me just check. It looks like, yeah, we can see your screen now.
Okay. Can you see the IDE of just, there shouldn't be nothing on, I'm just in the source directory.
Yes, I can see it.
Okay, great. So all of my project was just in this Turtlebot 3 wall following package. And the Python stuff that actually had all the classes were in scripts. And the first thing I had was just a control class. And anyone who's done the ROS Python Basics course might recognize this class. It's very similar to the robot control class that had published to the command velocity topic and subscribed from the scan topic. It's very similar to that, except I broke those down even further, where I had everything that dealt with subscribing to the scan topic as its own class, and everything that published to the command velocity topic in this Turtlebot 3 command velocity class. This Turtlebot 3 control class you're seeing here, it just initiates a ROS node that publishes and subscribes to the command velocity and laser scan topics respectively. So that's just with the constructor here, and then it'll call the constructors of those classes, which we'll go into now. Just, you might notice all of my programs have this if name equals main. That was for all the ones that have class as the final word in their file names. Those were just a little bit of test code for me to be able to make sure that the classes worked as intended. So starting with the laser scan class, this just has a single Boolean in its constructor that just says whether or not I want to create a node, like a unique node for this to do some subscribing to. Or if by default, I'm not going to, but if I just wanted to test, I would just say subscribing node equals true and not have to worry about creating another ROS node. Inside the class itself, there's this laser message attribute, which is just of laser scan. And that's where I'm storing all the messages I receive on the scan topic, which I'll get to shortly. Before I do that though, just after initializing, I call this wait for laser ready method. And what that does is it calls this wait for message program, and it waits 20 seconds before it timing out, where if I don't get a new message from the scan topic, I get an error, an exception, and I just say I didn't get a message, and I know that I haven't gotten a message recently from the scan topic. So either the scan topic doesn't exist, or I'm failing to receive messages from it.
That's a really good that's a really good way to do it. Instead of, because I usually recommend people when they start connecting to the real robot to check that the scan is working with the ROS topic echo of the scan. But with this, you avoid it, and it's part of your program, and you know that you're getting your laser like automatically with this class. That's pretty good.
Thanks. It also ties in with just when I have this first laser scan message, I know it's up to date after calling this method, because at least from what I'd noticed in the live demonstration, the number of readings, like the size of the ranges list, would differ. In the simulation, I think it was 360, but in the live lab, it was 720.
Yeah, it's just double.
So instead of just having to change it every time, I just made these other attributes that would get the range, like get the number of laser readings, the size of the list, and with the assumption that the rear, like the first laser reading in the list was directly behind the robot, I would assume the full 360 degrees. So in front of the robot would be the middle of the list, the left of the robot would be a quarter of the way through the list, and the right-hand side reading would be 3/4 of the way. And finally, I just have this subscriber that calls this laser callback function every time it receives a message, and that just updates my laser message attribute. You might have noticed a couple of these identifiers, or the names, have underscores at the start. Python just implements this thing where if you have 2 underscores for a method or an attribute, that is it's private. It can only be seen by the class itself or all of the methods. So I can't go into laser message like from, say, my main program and start writing values to it. I just like to have that sort of protection.
Right.
And then the rest of this class are just a number of getters. This one gets the smallest laser reading. This one gets the front, the left, the right, behind. This one's a specific one, and just does some checking to make sure we don't exceed the bounds of the laser readings. And finally, we get the full list of laser range readings. So that's the laser subscription to the scan topic. This Odometry class for the action server subscribes to the Odom topic, and it's very similarly structured, which we'll get to. And then there's the publisher, the command velocity publisher. What this does is it's similarly structured. There's no checking for making sure the topic actually exists like the scan topic. It just will publish once we've got a number of connections, which I'll get to. So in this one, I've got this vel command attribute, which is the message that I'll be publishing to the command velocity topic. And the way I have it done is in this set velocity command, you can set the linear speed and the angular speed. So the X, the forwards, backwards speed, and the Z, angular Z, the rotation speed, based on this set velocity command. But because this would, to guarantee reliability, might not work if you tried to publish the message just once. So again, from the robot control class, I implemented something very similar where I waited until my publisher was actually connected to the topic or had more than 0 connections before attempting to publish. Otherwise, I would just wait. So you would know if you weren't successful in publishing to the topic, because you would just get blocked by this never-ending loop until you hit Control C, which again was also from the robot, similar to the robot control from the basics course, where there's just this flag that's initially false, but once you hit Control C and call this shutdown hook, it just sets that to true. So inside any sort of program, if I hit Control C, I would just stop whatever motion I was executing, and that would be another way to stop the robot, basically, or to stop, to get out of this like infinite loop or something.
So why did you do this? Were you having problems stopping the robot without implementing this, or you just wanted to create this to like keep it structured and nice?
Mostly the latter, having a really heavily structured approach, and just so I would know what action had actually caused like getting out of the loop. I mean, I don't say it, but the only thing that would stop it from executing just some motion would be this Control C flag. And at least according to some of the documentation I had found, it was slightly more reliable than having an on calling like is shut down, checking if the publisher or the node itself was shut down. So again, it was just more for more reliability.
Yeah, and plus you have the added perk, let's say, that sometimes when you end the program, the command vel is still publishing, so the robot will keep moving, forever until you send it a 0 value. So this is a good way to avoid that too.
Yes, yeah, I still have it. I was meaning to implement an actual stop, but because this, the Control C also is used in this publish velocity command, where we try and publish messages, and if we don't succeed, we'll be sort of stuck in this loop forever. Right. So Control C is a way to just get out of that as well. So both this and the subscriber, laser scan subscriber, just make up basic control of the Turtlebot, and I use these in my wall following and in the actual find wall service, which I'll get to now. With the wall following, I inherit that Turtlebot 3 control class and execute its constructor. And also, just in an effort to have a bit of robustness, instead of relying on a single reading, a single right-hand side reading, I tried to have like a little bit of a beam, like a fan beam, that would read a number of readings that were surrounding the right-hand side and directly in front of the robot, where I would look at the minimum.
And how big is that section? How big is like the section on the right and the section in the front, like compared in relationship to how long that message is? How did you determine that?
So by default, I just have it as 10, and that is based on the resolution of the laser scan messages. So if there were 720 like readings, like in the list of readings in ranges, it would be a full, it would be half a degree, would be one, like a fan of 1. So by setting it to 10, and in this case, it's a 720, 10 would be 5 degrees from right, the middle reading was the right reading, like to the
Mm-hmm.
right of the robot.
Yeah.
This value of 10 would be 5 degrees plus and minus relative to the center of the robot. So
Okay, I understand.
yeah, I made sure it wasn't too large. I limited it to 15 degrees based on the size of,
Yeah, that
like,
makes sense.
if it was 720, this number would it wouldn't be larger than 30. If it was 360, this number couldn't be larger than 15.
Okay.
And then I'll get to those ones. The actual method itself of following the wall is just here, where I get this program follow wall is to this is meant to be called inside a loop, and it will first get the right laser ranges and then get the front right laser ranges using the get laser full we saw in the laser scan class, in the laser scan script, laser scan class script, sorry, and extract the range based on the list of ranges that are surrounding the front and the right respectively by the fan beam width. So if we had 10 here and the laser front pos was 360, this would get the laser scan ranges that were between 350 and 370. And for the right hand side, it would be between 540, so 530 and 550. It would look at a list of those basically, and then it would just use the minimum of that. In these conditionals. First, we check if the front wall is less than 0.5 meters, and if it is, we basically just turn the robot left to avoid the wall. Next, we check to make sure that the right-hand side reading is not larger than 0.3 meters, and it's not infinite in case you were missing messages. I would just ignore infinite readings. And if it's larger than 0.3 meters, I would turn the robot to the right.
To the right, yeah.
And if we're too close to the wall, less than 0.2 meters, I would turn the robot left. I made it so it would turn faster if it's approaching the wall quicker, like instead of just to try and keep it so it goes straight for longer periods of time, where in reality I was having it so it would sort of oscillate between, oh, it's too close, and then it would overturn, and then it would be too far, and then it would turn to becoming too close again. And finally, if it's none of these three things, just travel straight ahead at 0.8 meters per second. And if you call this inside the wall, call this class or this follow wall inside a loop, it would just follow the wall forever, basically. So that was like the part one, essentially. Yeah, sorry it took so long to get to that, but hopefully, no problem. Building up with all these classes, it did make it a little easier for me to.
And it's so easy to understand this way. So I like how structured you are. How do you have the two classes for the command vel and the odometry, and that way you can use any of those in your main program. I think that's really well done.
Thank you. I had used this actually to, like, I'd imagined in future ones I would structure like any sort of publisher or subscriber or what's similar to this, where I would just have a class and then it would sort of be out of sight, out of mind. I could just grab a message or publish a message whenever I needed it, which I tended to do a lot with the.
So the next part would be to use a service to find the closest wall, correct?
Yes, the closest wall or just the closest object. There wasn't any like whatever the nearest laser scan reading was. I would get that, and this service, what it does is it grabs that. It also inherits the Turtlebot 3 control class, and I would work out where the minimum was. I would rotate the Turtlebot so that it was facing where that minimum was. I would move the robot straight ahead until it was facing that point. And ideally, it should approach the object at 90 degrees. Like, it should be facing the wall. So then I rotate the robot 90 degrees left. And that's the service, basically. That's what all these commands do. So this face closest obstacle that looks for the minimum laser position.
And did you use a range, like in the looking for the right and the front, or did you just use like, are you looking for one value?
I'm looking for, I looked for one value. So I got this inside the laser class. There's this get minimum laser pos, get the minimum laser position, which it just gets the fullest ranges. Yeah, and it will return the position. Like, it'll be a number, in this case, between 0 and 719. And then I would use my knowledge of the size of the list to rotate to know how far I needed to rotate the robot accordingly. So if I got like if I got a 0 reading from the minimum laser position was 0, the self laser front position is 360. So 0 minus 360 times 360. That's a bit confusing. Then so this would be minus 360 times by 360 divided by the size of, like, the size of the laser ranges list, which is 720. So times it by a half. So I would rotate the robot minus 360 times a half. So minus 180 degrees, basically. So I would turn the robot around, and I would sort of state how much I'd actually, where it was, the minimum closest orientation. So I would just know which way the robot turned, and it was mainly for debugging, just working. So now, once I know the minimum, I rotate the robot, and nothing terribly advanced. I just had I would set a rotation velocity based on how far I wanted to rotate and for how long. So this rotation time is just configurable. So I just set it to 10 seconds. So 180, if I wanted to rotate 180 degrees, I would, 10 seconds, it would be 18 degrees a second. I publish that, get the robot to wait for that period of time, so for 10 seconds, and then stop the robot, and I know it would be facing the closest object. Then I would move the object towards the wall. So just, again, getting the front laser reading, and once it's less than 0.3 meters, I'd stop. And then I would rotate the robot 90 degrees counterclockwise looking down, so to the left. So then I'd be ready for wall following on the right-hand side.
And then your service just says true, right? Like, you've found the wall.
Yeah, it'll just have this log. And this service actually has its own message. You had to make your own message for this. So the message was, the service message was just an empty request, and the response is just the Boolean wall found. So I, need to ensure that was made in the CMake list. Just here.
Right. And with that Boolean, you can start, like, once you found the wall, you can start then your following like behavior.
Yes. So this service gets executed first. It'll find the wall, and then it will begin the wall following behavior that we just seen before. Finally, there's the action server.
And this is for the odometry.
Yes. So there's, for the odometry, we're subscribing to the odom topic. So it's so I just made another class for it. It's very similar to the laser scan class, except it's got just a few more getters. It's still got that wait until we get a message from the odometry topic. And then we just execute this callback that we can use to get the odometry whenever we need it. And I just use this in the action server. So in the action server, I forgot to mention the service creates its own, it has its own node, and I forgot to mention there's the name of the service itself is called find wall, just here as instructed. So we create that in the constructor of the find wall class. We do the same thing in the action server class, where we make the action server, we set the callback and the message that we are receiving. And also for the action server, because we want to get feedback every second, I just have a publish rate of 1 hertz to get the feedback so we can see it. So in the action server, once it's called, we execute the callback. We have this success flag, which just checks that the client hasn't preempted the action, because it can be canceled at any time. And we initialize these feedback and result attributes, which are just initialized in the class.
Right, and the current total is the whole distance that's been moved?
Yes, yeah. The total distance that the robot has been traveling since starting its wall following motion.
Okay.
So
not starting from when you start to try to find the wall, but once you found it and then you start following the wall.
Yes, yeah.
Okay, I understand.
And these feedback and so those messages you would see are also custom messages. The odom record message. I'd seen in the past people had used the point point message. I just used pose 2D just because it had the nice XY theta. You can use the point one. It makes no difference except for the fact that there's a Z there, and it actually does make things probably smoother and better.
Yeah,
and
less fields to worry about, no? Because I think point says a bunch more that you actually don't need.
No, point is the same. It's just the odometry, when you're getting the position, it is a point object. It is a point message,
So
and I'm writing that in my result. Like I can get that directly from the odometry message, and just plug it into the result, like my list of odometries. But with the pose one, that doesn't quite work. So I had to break it apart and assign them separately, which
feed it back into. Okay.
Yeah. So after this constructor will initialize what the feedback and the results are going to be, the node that's using the action server, the name of the action server itself, and how fast we are getting the feedback. And when we get a goal, we execute this goal callback, which assumes we've got this success flag, which just assumes that the client hasn't preempted the goal, and we just reset the feedback and result values to make sure there's no debris from the previous action server request, or action server goal rather. And then we start to record the odometry. So for the first two readings, I just get the pose, and I don't use them for anything else. It just I get the pose from the odometry, which gets the odometry position, which is in the odometry class. It just returns the position part of the odometry message. I also just initialize a pose message, because position and pose, these are two different classes, so I couldn't quite write them directly to one another. It would throw an error. I get the X and Y coordinates because the Z coordinate is not relevant. It's just going to be the constant for the whole Turtlebot's motion. And then I get the theta angle, which is just the yaw angle. And I get that using the Euler from quaternions method, just from transforms. So it converts the quaternion in the odometry message into a roll, pitch, and yaw. And I just am interested in the yaw value, which is the theta. Roll and pitch are similar to the Z, where they're going to be constant or not relevant for getting the robot's poses. So every time I call that get pose from odom, I get the current X, Y, and theta, and I append that in the result. So every time it gets called, it grows. That's the list of odoms.
Keeps going. Okay,
yeah. And then I have also this lap complete flag, which just like checks to make sure the lap's not done. And then I have this loop that will just be running whilst the robot is executing its wall following motion. Every second it will update its distance feedback. So what it will do is find the distance between the current two latest odometry, like position measurements in the result field in the list of odoms, and use Pythagoras' theorem to calculate what the distance is traveled in that second, and then add that to the current total in the feedback. And then once I've computed that, just return that as feedback, publish that as feedback. Then there's the 1 second wait. Then I append the next odometry measurement, and I check to make sure this latest odometry measurement hasn't checked to make sure the lap's complete, which happens when I'm within 0.2 meters of my starting position. So if I'm within 0.2 meters in a circle anywhere around that starting position, I've completed the lap, and we will get out of the loop. Alternatively, if the client preempts the goal, we will get out of the loop and we say the goal's been cancelled, and we just drop the odometry, and we set this to false. We clear the success flag. Then we get to the end, and if this success flag is true, we will publish the list of odometries, and if it's false, we just exit the callback and we return to we don't return. This runs in the background, or you can run it in the background and do other things, return to doing other things.
Right. Do you, hey Sam, do you mind, now that you sort of explained the 3 parts, because we have like 10 more minutes in the slot that's available for the.
Sorry,
do you mind
demonstrating?
We can start if you have something else to add while it's running, so we can check that.
Yeah. I think this last one. So these are all the actual. So the service server, the action server, wall following. There's finally the main program that uses all these things, which I can explain. I'll explain that in the background, like whilst it's running. Yeah, I should get this going. Might just update this to make sure it's still right. Okay. I think I just want it to be full screen so we can see like
Yeah,
the
yeah.
messages getting the ROS log information, not getting going to the next line.
Looks like we have an issue there with one of the cameras.
Yeah,
Let me go and check it real quick. And
I might reload it as well, just so I found that worked before.
so now it's looking for we saw that it was looking for the wall.
Yes, so it said that the closest obstacle is 154 degrees counterclockwise,
Right.
so it's going to turn 154 degrees to the left, and then it's going to move forward until it's 0.3 meters away from the wall. And then we are going to call the action server.
Right, and it starts recording the odometry.
Yes, and we can just have a look to see the feedback topic and see if it's actually increasing. No. Okay, so you can see it there. It's just going up 0.6.
Right, and the Turtlebot right now it's moving, correct?
Yes. So let's see if I can. So yeah, we can see the Turtlebot just moving.
Yeah.
Don't know where the right camera is.
Yeah, I'm sorry about that. Must have gone out, but fortunately we have two.
Yes, very fortunate. So it is a little slow. So it's going to be following. Once it detects the wall ahead of it, it'll start to turn left. You can sort of see what I was trying to do with this bounds checking, having like a fan instead of just a single reading, where it's a lot of the time it's like turning right and then it starts to shoots and then it goes straight and then turns left fairly quickly. I guess I'll just briefly cover the main process. I just call it the client because it's the client for the service and the action server. So if they've seen the ROS Basics in 5 Day, they might recognize all these little names based on the state of the action server. But before we use these, we call the find wall service. We create we wait till it's connected, so we'd stop here. Then we would establish a client, and we would send through that the request, and then we would just be waiting here until it's found the wall. Then once it's found and it's ready for following, we would call the action server. And this is just this stuff. It's very similar to what's done in the ROS Basics tutorials. And then we get the state from the action server. And so in addition to the control C that we saw before, we're also checking the state result. And if we're done, we will stop following the wall. And with the list of odometries, I just printed them. I didn't really know what else to do with them.
Yeah, I mean, just to display them. Is the lab done? Oh, there we go. We have the two cameras now, and it's like half there, no?
Yeah. Yeah.
And we can still look at how long it's traveled.
Yeah, we can see how far it thinks it's traveled. So, So 5.3 meters.
Nice. So that's the whole combination of starting with the looking for the wall service and then doing the wall following program and using the action server to record the odometry. This is all inside one launch file, right?
Yes, the main launch file. I guess I'll just briefly, I might touch on those at the end. I don't want to miss seeing what happens.
No. This is the nice part, and it's really precise. Look at that. It's
hesitate to say precise, but thanks. Oh, did it stop? I think it's done. it's finished.
Right on.
Oh, the X readings are very large, but I guess maybe that's where they're just referenced to the Odom frame. So
Right. So yeah. But then this is x the x, y, and theta that it's ending at.
This is the full list of
Oh, this is
odometry.
the
So this would be
entire sort of
yeah,
path that and this is every second that is taking this, right? You said
yeah,
30
every
minutes?
second. Yeah.
Wow.
Yeah, I kind of wanted to see like it's a finishing wall lap complete publishing list of items, but it's just a single message.
Did
I mean,
it stop moving?
yeah, so it should stop moving, and the main process client will actually end. Just because that's we get out of this loop
right.
once the action server is done, and we stop following, and then we print the list of odometries. I didn't quite know what to do once you'd finished, like to indicate, hey, we're done, we've completed a full lap.
Yeah, I mean that's
so I just had that.
This is a good way to go about it. Like, hey, look at this list, and then after that, you could even build upon that. You know, if you really want, you can like plot it or feed it into some way to analyze a ton of labs and how to optimize it. You can do so much with this, especially the way you've structured it. I really like how you have this whole setup. And
thanks.
I have a question about that actually that I think is really interesting for listeners that want to sort of take your example and start building their code this way, and that it's which. So are you done presenting your code?
Yeah, all the scripts, which I think is the main part, is
okay.
all done. They're in the launch. There's also the launch files. They're pretty. For this first one I'd set up was just for testing purposes, but the main launch is the one that calls these other three launch files.
Oh, that's a good practice too, to like put. I tell myself, put little launches into big launch, so you have a main launch file that is calling other launch files, not nodes specifically, just to keep it sort of structured, like you said. Like I'm just making an emphasis on how well you're doing your structuring, because otherwise it starts getting confusing, and this way you keep it under control.
Yeah. That was a big thing, like having it well structured. And if I'd gone away for a bit of time and came back, or if I wanted to develop them further, that was I'd be like, oh, okay. It would be I'd be able to get myself back up to speed fairly quickly, and I could build on these like later down the track, like with even just using these in future, like for other like projects or applications. That was sort of the mindset I was trying to have.
And this is from the start, right? So my question was, do you start sort of thinking about how to build your classes and then work on your main program, or do you work first on the main program and think about the sort of class you'll need to add to that main program? What was your process there?
More the first, the former. I like to have the nitty gritty nuts and bolts, like basic things working. So sometimes, I think over the course of this even ROS project, I just become a bit more adept into thinking about how I could put it together as a class. Originally, I would just have like just some code that would do something. Like with wall following, I didn't have any classes or any sort of like hiding a lot of the implementation. Like the class deals with how I do something, like internally, but it was sort of I found it a bit insurmountable once I had a lot of these big long bits of code that were sort of having to do the same things, and I wanted to take like real advantage of like hiding a lot of the like once I'd done it once, then I never had to really think about it again.
Yeah. And it becomes sort of a Swiss Army knife for commands and things that you will need. You know, it's like your class becomes like this toolbox that you can take from as you go along in your main program.
Yeah.
Nice.
Well, yeah, the main program was it was kind of oddly shocking how like kind of I didn't really need to think about too much like how something was getting done. I just made I'd make like a method or something in the class.
Yeah.
And then I didn't really have to worry about it.
Yeah, and the way you read that main program is almost pretty much English because you have that structure so well. So you like really can just go line by line and say like, oh, this is what it's doing. This is what it's doing. This is what it's doing. So great work in that regard.
Thank you. And thanks to anyone who was listening. I'm going to stop sharing now. If anyone was watching, I'm very glad you tuned in.
Yeah, and they'll be able to see your
my screen or like my code.
Yeah, definitely. They'll be able to. Oh, sorry.
I did feel like I sort of breezed over a few things. If people did want to have a better look, would that be possible or
absolutely,
not necessarily?
Yeah, I mean, we just need to. I mean, either you guys that are watching that want to learn more, you can comment on or if you want to talk about something that you think is important that will add to your explanation, we can go over it now. There's time if you want. Or if not, like you said, they can get in contact with you and through the comments and we can create. That's part of the putting it on YouTube. Is like we create a community and maybe someone that's working on his ROS project for this course will look at yours and be like, oh my God, this is a great idea. Maybe I'll implement it. Have a question and that's sort of what we're trying to. A side effect of what we're trying to do here with these students' presentations. But let me see if I have some questions here that a couple more that I wanted to just kind of pick your brain with it. One
sure.
That I thought was that you're using the right side of the robot and the front, which means that this will be a counterclockwise direction, right? Yeah, because it'll always be looking at the right, like stuck to its right. What would you need? What would it take for it to go the other way? Would you have to do a big modification in your code, or would it be what would be needed in order to say like, oh, now let's go the other way?
If I wanted to strictly go like the other way, or if I wanted
the option of one or two, you know, like.
I don't think so. I think all I would need to really change would be that wall following class.
Yeah, you would just instead of adding a right one, get a left one, no, and then instead of in the wall service, instead of, I guess it would be instead of rotating to the left, it would be rotating to the right, so you can.
Yeah, perhaps I could have an argument that said, you know, which way, right or left, and based on that argument, that could follow it that way. Although changing on the fly would be a little tricky, I'd imagine, but making it so.
But now with the implementation of your classes, it will take you a lot less effort. That's the point I'm trying to get at. Because we always try to stress to our students, you know, to think in this mindset that in the beginning it might seem like it's more complicated, but as you start building upon it, it actually becomes easier.
Mm.
And I mean, other than that, I thought like it was an amazing program. You went above and beyond, especially with this class structure, and we saw that it worked correctly. Thankfully, the cameras came back a little.
Yeah.
This is part of working with a real robot, especially with a remote one. That you run into issues that sometimes you don't find in the simulation, and we think that this is part of learning robotics. This is the last step to sort of know that the code that you're writing affects the physical world, but the physical world will affect the world that you're writing, the code that you're writing.
Yeah.
And
Yes. Yeah. We almost suffered from that, actually, the Odom thing.
Yeah.
I was very worried about that.
Yeah, we had, and this is something on our side that I'm going to work on. Let's just put it out there, because we had a presentation earlier where sometimes the odometry doesn't get published, and this is an issue with our motors, and I'm going to look into that so we can make sure that you're always receiving this odometry, and yeah, that's another student that happened to him the same thing, and he made a whole different. And this is the good part about the presentations, that you see how people deal with this. This other guy that presented sort of came up with a way to obtain the odometry from the command vel topic. So he started to taking the command vel and doing some work with it in order to sort of integrate the odometry, because he wasn't seeing that odometry topic, which now thankfully we see it, and yeah, we'll just keep improving on that, and it's just part of the learning process.
I was thinking, I thought something like that might have been a bit beyond the scope of this ROS check, but I was thinking something similar to
this. Is like your structure, class structure. That's way above this the scope of this this ROS check, and what I'm really glad to see is that people consistently go above it, and there's like things that I wouldn't even think of like people that are doing solutions this way, or people structuring this way, so you can just build a really complicated program with your classes. It's just really great to see all of the solutions that people are coming up with. And well, if there's nothing else, I mean, is there anything else you want to share with us?
No. Thanks everyone for tuning in. That's all I've got to say, really.
Well,
thank you for your time, actually, as well.
No, yeah, thank you for presenting this great project, and this is now just for you guys that might be watching. This is a great project that you can test your skills with all the basics that ROS is offering, and so I encourage you guys to take a look at our course and take a try with this ROS check, because this could be you and showing your skills and showing your presentation and what you've been able to do with this project. So you guys are up next, and thank you, Sam, again for your time, and we'll continue this, and next time we'll see if you can continue with another course, maybe another project, and we'll go from there. But other than that, thank you everyone for coming and watching this. We'll see you for next presentation, and thank you, Sam.
Thank you.
All
right. Have a good night.
Goodbye, everyone.